Let's talk about something we all take for granted every single day, the incredible, almost magical speed of our computers and phones. We're talking billions of operations every second. But how? How is that even possible? Well, we're going to pull back the curtain, because the story of how we got this fast is just a masterpiece of clever engineering. And I'm not kidding here. Just think about that for a second. The little device in your pocket has more raw computing muscle than a machine that used to fill an entire room just a few decades ago. It feels impossible, but it's not magic. It's all about engineers finding brilliant solutions to one fundamental problem. You see, here's the secret. At its heart, a processor is actually kind of simple. It's like an old freight steamer. It does one thing, then it does the next thing, and then the next. It's a very reliable but also very slow, one-step-at-a-time process. So the real puzzle was, how do you make that freight steamer feel like a fighter jet? This slow, four-step dance is called the classic fetch-execute cycle. Every single instruction your computer runs goes through these four phases: fetch, decode, execute, and write back. Now, in the early days, the CPU couldn't even start fetching instruction number 2 until instruction number 1 was completely finished. Talk about a traffic jam. That was a huge bottleneck. So to break that bottleneck, engineers had a real eureka moment, and they borrowed a brilliant idea that had already revolutionized manufacturing more than a century ago. They decided to turn the CPU into a high-tech assembly line. And this game-changing technique is called pipelining. Think about it. Instead of waiting for one car to be totally finished before you even start the next, you have different cars at different stages of the assembly line all at once. Pipelining does the exact same thing for computer instructions. And honestly, this is one of the most important breakthroughs in the history of computing. So this is what it looks like in action. As instruction 1 moves from the fetch station to the decode station, the fetch station is now free, so the CPU immediately starts fetching instruction 2. And as they both move down the line, instruction 3 gets fetched right behind them. Now here's the key. The time to finish any single instruction is still the same, but the overall output, what we call throughput, the number of instructions you finish per second, just skyrockets. And of course, this idea just keeps building on itself. Engineers thought, okay, one assembly line is great, but what if we had more? And that's the massive leap from what we call scalar to superscalar processing. A scalar processor has that one pipeline, but a superscalar processor, oh, it has multiple parallel pipelines, what we call execution units. It's like having totally separate assembly lines for different jobs, all running at the exact same time. All right, so now our CPU has these blazing fast, multiple assembly lines. Problem solved, right? Well, not quite. In fact, all this new speed created a brand new problem, a new bottleneck that was so bad it threatened to bring everything to a grinding halt. So here's the new dilemma. Your CPU is now this hyper-efficient factory. But a factory needs parts, in this case, data and instructions. And it gets those parts from the main memory, your RAM. The problem is, the RAM is like a slow, distant warehouse. So your super fast CPU ends up just sitting there, tapping its fingers, waiting for the parts to be delivered. All that incredible speed is just wasted. The solution is just genius. If the warehouse is too slow and far away, you build a small, secret stash of the most commonly used parts, and you keep it right next to the assembly line. In computing, that's called cache memory. It's built from much faster and way more expensive memory, and it's located right on the CPU chip itself. And here's the simple way it works. When the CPU needs a piece of data, it checks the super fast cache first. If the data's there, boom, that's a cache hit, and it gets it almost instantly. If it's not there, that's a cache miss. Then, and only then, does the CPU have to make that slow, painful trip all the way out to the main memory warehouse to get it. So why is this tiny little stash so effective? Well, it's all because of a principle called locality of reference. That's just a fancy way of saying computer programs are creatures of habit. They tend to use the same pieces of data over and over again in a short period. The cache gets incredibly good at predicting what the CPU will need next, and the result? A hit ratio of 90% or even higher. That means 9 times out of 10, that slow trip to the warehouse is completely avoided. It's a massive performance win. Okay, so we have our assembly lines, pipelining, and we have our super fast part stash, cache memory. Now let's put these pieces together and take a look at the blueprint for a modern high-performance processor. When you put it all together, it's like a bustling city.
You have an instruction unit acting like a traffic cop, fetching instructions and directing them to the right places. It sends them off to multiple, specialized execution units. Some are math wizards, others are experts at talking to memory. Then you have layers of cache, L1, L2, L3. Each one a bigger, slightly slower stash. And get this, there's even a special unit whose only job is to guess what the program will do next, just to make sure those pipelines never run dry. The whole thing is just a beautiful symphony of optimization.
So we've optimized this single engine to an unbelievable degree. But the quest for speed, it never stops. So engineers ask the next logical question. If one of these amazing engines is this good, what happens if we put several of them in the same machine? And that is exactly what a multi-core processor is. We're not just talking about multiple assembly lines now. We're talking about putting multiple complete factories, called cores, all onto a single piece of silicon. Each one of those cores is a full-blown superscalar CPU. This is what lets your computer browse the web, play music, and run a dozen other things all at the same time so smoothly. Now, these cores can work together in a couple of ways. On your laptop, you've probably got symmetrical multiprocessing, or SMP. All the cores are equal partners sharing the total workload. It's perfect for general use. But for more specialized jobs, like in a graphics card, you'll often see a master-slave setup. One master core acts as the boss, handing out thousands of repetitive tasks to the other slave cores. That's how they can handle the immense calculations needed for something like rendering a complex video game world. So we went from a single, slow, step-by-step process all the way to multiple parallel factories on a single chip. It's an incredible journey. Pipelining, caching, and multi-core processing, those are the three pillars that modern speed is built on. But the quest never ends. So that leaves us with the big question. What's the next great bottleneck? And what ingenious solution are we going to invent to smash right through it?